Dear participants, welcome to 9th International Symposium on Multidisciplinary Studies and Innovative Technologies. The conference is supported by IEEE Turkey section and also supported by Tokat Kahramanpaşa University. We are in session 2.2 now, and we have 7 papers to be presented in this session. Each participant will have 10 minutes to present their studies. The title of the first paper is Integrating Artificial Intelligence into Modern Education Models for Interactive Multimedia and Personalized Educational Materials.
Hello.
Hello,
My name
you
is
can...
Donika Vocheva. Yes, just a second.
Okay.
Do you see the presentation?
Not yet.
Not yet.
We see your screen, but not presentation.
Okay.
Now we can see.
Also, now you can see now.
No. Now, yes, we can see.
You can see. Okay.
Yes.
So I can start.
Yes.
Hello, everyone. My name is Donika Vocheva, and I'm Associate Professor in Veliko Trnovo University, Bulgaria. Today, I'm going to present you a paper with title Integrating Artificial Intelligence into Modern Education, Models for Interactive, Multimedia, and Personalized Educational Materials. This paper explores AI-driven models that support adaptive learning environments useful for the individual student's needs, preferences, and learning styles. The study presents current trends, tools, and practical applications of AI in educational content development, as well as a conceptual model for implementing AI-based personalization in digital learning platforms. The findings highlight the potential of AI to bridge learning gaps, enhance student engagement, and support teachers in delivering more effective and inclusive education. The main objectives of the study are to present the key AI technologies useful in the educational context with a special focus on generative artificial intelligence, to investigate the characteristics of the new generation and the impact of the digital environment on the learning styles, to analyze the possibilities for creating multimedia and personalized learning materials using AI, to identify and describe effective models and tools for developing interactive content, to discuss the advantages and challenges of implementing AI in the learning process, and to formulate recommendations for the effective and ethical use of artificial intelligence in education. The study is based on an interdisciplinary approach that combines methods from the fields of educational sciences, computer science, and artificial intelligence. The goal is to develop a comprehensive understanding of the potential applications of AI in modern education through the analysis of theoretical concepts, best practices, and available technologies. The main methods used in the paper are literature review, qualitative analysis of educational technologies, and comparative analysis. The methodological framework is flexible and open to further development, allowing for future empirical research and practical experience in real educational settings. The digital generation includes children born after 2010. This is the first fully digital generation, born in a world with mobile devices, internet, social networks, and smart technologies. They exhibit specific cognitive, communicative, and social characteristics that significantly influence the way they perceive and acquire knowledge. The key characteristics include high digital literacy from an early age, short attention span, visual and interactive learning orientation, preference for personalized competencies, and highly developed multitasking ability. Next. In response to the technology environment in which they grow up, children of the digital generation develop new patterns of perception, attention, and knowledge acquisition. This brings the need of a significant reassessment of traditional pedagogical approaches and a transformation of the educational environment. From passive to active and engaged learning, students are no longer satisfied with merely listening to lectures or reading texts. They prefer learning through experience, participating in simulations, solving case studies, creating their own projects, and interacting with digital environments. From single source to multi-channel learning, students use multiple sources simultaneously: text, videos, podcasts, interactive maps, forums, and others, and expect integration among them. AI can support the gathering and adaptation of these resources according to each learning's needs. From ready-made learning to discovery-based learning, the new generation prefers to experiment, play with information, seek solutions independently rather than simply memorize presented facts. From standards to personalized learning, increasingly important is the ability of learning to adapt to the individual style, pace, interests, and strength of the students. Artificial intelligence has the potential to support precisely this type of personalized education. From linear to non-linear content consumption, unlike previous generation who approach learning materials sequentially, digitally native students often navigate chaotically between topics, formats, and resources. This requires the development of flexible, modular, and well-structured resources that allow for individual learning pathways. Changes in the learning style of digitally native children require comprehensive reassessment of the content, format, and teaching methods in modern education. There is a clear need to create a new type of learning materials that are interactive, multimedia rich, adaptive, gamified, and creative and open-ended. In the educational context, several key types of AI technology show significant potential: generative models, adaptive learning systems, natural language processing, intelligent tutoring system, visual recognition and analysis, and automation and data analysis. Key application of generative AI in education include automated creation of learning materials. Generative models can develop texts, explanations, examples, and exercises tailored to students' knowledge level and interests. This enables an individualized approach and reduces the time teachers need for lesson preparation. Generation of visual and multimedia resources. Educators can produce illustrations, infographics, animations, and videos that make educational content more engaging and easier to understand. Personalized interactive exercises and assessments. Generative AI can formulate questions and tasks that adapt to each learner's progress and needs, offering immediate feedback and encouraging deep understanding of the material. Virtual assistants and chatbots, these tools enable natural language communication and support students in problem solving and understanding complex concepts in an accessible and personalized way. And creative content generation, students can be encouraged to create their own stories, projects, presentations with the help of generative AI, fostering creativity and critical thinking. In conclusion, generative artificial intelligence provides a powerful toolkit for transforming educational content, making it more adaptive, interactive, and motivating for the new generation of learners. About intelligent tutoring system, they are complex software solutions that utilize artificial intelligence to provide personalized support and instruction, simulating the individualized approach of a human teacher. These systems analyze students' behavior and progress and dynamically adapt the content, difficulty level, and teaching methods based on their specific needs. The key features are knowledge analysis and prediction of learning difficulties, adaptation of learning content, real-time feedback, virtual assistant and support bots, integration of multimedia and interactive elements. On the next this slide, you can see a comparative analysis of some popular intelligent platforms according core functions, application area, personalization level, and supported technologies. Adaptive learning is an educational approach in which learning materials, tasks, and methods dynamically adjust to the individual needs, abilities, and preferences of each student. This enables personalized learning that increases effectiveness and motivation by allowing each learner to progress at their own pace and in the most suitable way for them. Key principles of adaptive learning are behavior and progress analysis, dynamic content adjustment, personalized learning path, real-time feedback and support, and motivation through gamification and goal setting. Generative models allow for the automated generalization of textual, visual, and audio content. They are used for generating interactive texts, creating images and illustrations from textual description, developing animated videos and virtual scenes, and producing voice recordings through text-to-speech synthesis. Adaptive learning systems can analyze learners' progress and behavior data to adapt content in real time. This enables the creation of personalized learning pathways through intelligent tutoring system, dynamic generation of exercises and quizzes, and automatic adjustment of difficulty levels. Multimodal approaches simultaneously process different types of input data, text, image, audio, to create rich educational content. Examples includes educational games incorporating video and speech, interactive presentations with built-in question and answer chatbots, simulations in augmented and virtual reality supported by AI. Interactive platforms with embedded AI. Platforms such as Khan Academy, Canva, Magic Design enables educators to create engaging lessons with minimal technical skills. These platforms offer templates with auto-filled content, integration of video, audio, and interactive components, and built-in chatbots for feedback and assistance. Based on this research, in the future, the authors plan to design and develop a hybrid model for creating personalized, interactive, and multimedia educational materials. The model will combine three main components to create personalized and engaging educational experience for students: adaptive AI core model or personalization engine, AI multimedia generator, and interactive learning interface. Thank you.
Thank you for your presentation. Are there any questions? Okay, let's go on with the next paper. The title of the paper is A Multimodal CNN Approach to Static Object Recognition Using RGB and Depth Data.
Yeah, hi. Can I share my screen, please?
Yes, you can share.
So, is it up here now?
Not yet. We cannot see. Yes, now we can see and you can start.
Okay. Okay, thank you. My name is Idris Hussein. I'm from the AI department at the University of Kirkuk in Iraq. Today I present my paper, a multi-model CNN approach for a static object recognition using RGB and deep data. In my talk, I just go in a brief introduction, then the research problem, core research question, methodology contributions of the paper, and results, the conclusion, and the future work. The main goal is that the reliable object recognition is crucial for autonomous systems, especially for robotics. And the problem is in the real world, the light chains, shadows, and confusion textures are a big problem for the robotics to recognize the objects. So there is a need for depth data, which is provided from depth cameras for a second modality. For this reason, we go to the modality by using the depth maps with the RGB images. Each of them has advantages and disadvantages. For RGB images, sensitive for the lightning chains, shadows, and reflect the surfaces. For the depth map, like for fine details and poor performance. The problem is the single modality in both models lead to confusion and the higher reliable robotics perception. The main research question for this paper is how can the RGB and depth data be effectively integrated using a multimodal CNN architecture to maximize the accuracy. And the suggestion solution is to use a two-branch CNN architecture with intermediate feature fusion. The mechanism is each branch process on modality independently and then extract the features which are combined to make the classification. The proposed method is a framework to parallel branches, RGB and depth, run concurrently. The inputs are paired RGB image and depth map. The goal to extract the specialized features from the two branches and then concatenate the features vector to form a composite vector F, and the output pass F will be full connected layers for softmax classification. The multimodal CNN architecture, as we can see in this figure, consists of two branches. The first one is the RGB branch, and the second one is the depth branch. The RGB branch processes the color image data, and the depth branch processes the geometric depth map of the data. The RGB feature extraction using VGG16, the model are pre-trained on the image net data set. Then the feature extraction extract the features from the image. The output will be one-dimensional vector for the RGB features. The depth branch, the model will be a custom lightweight CNN, and the training of it will be from scratch, not pre-trained like the RGB branch. And the output will be also a vector, and it's independent from the first branch. The feature fusion will be obtained by concatenating strategy, by concatenating the first vector from the first branch and the second vector from the second branch, and the final vector would be input to the classification stage, which is used the softmax to classify the object. The contribution of this paper has improved several aspects. The first one is a multimodal architecture, which is proposed and validated of a robust two-branch CNN framework for RGB and deep data fusion. Hybrid backbone design, which is utilized a powerful pre-trained VGG16 for RGB and combined with a lightweight CNN depth efficiency. Feature fusion strategy, which is a direct concatenating strategy for feature vectors. And finally, the proposed method improve the efficiency by increase the accuracy of the model. The results, as we can see, that the proposed method, the accuracy is around 7% over RGB only, and also it's over the depth only baseline. The depth information I did as a second branch, and this will improve the accuracy of the model. And this table also shows the results using the metrics for object recognition for some objects from the data set. And those objects are the diverse objects, and also, as we can see, the model recognize them. As a conclusion, the research successfully validates that intermediate feature concatenation in a hybrid architecture is an effective strategy for RGB and depth data object recognition. The 92% accuracy confirms that the model improve the accuracy of the object recognition, and the solution is robust and efficient, making it high suitable for robotics perceptions applications in a static environment. As a future work, evaluate the model's performance in uncontrolled dynamic outdoor environment for object recognition, and investigating different fusion strategies like element-wise product or sum. Extend the methodology to instance segmentation or object tracking in video stream. And that's it. Thank you very much. If you have any question.
Okay, thank you for your presentation. Dear participants, do you have any questions? Okay, thank you. Let's go on with the next paper. The title of the paper is AI-First Operating Systems Rethinking OS Architectures for Machine Learning.
Can I share my screen?
Yes.
Okay. Can you see my screen?
Not yet.
Can you able to see this one?
Not yet, but I think it's coming here. Yes, now we can see. You can start.
Okay. Okay. So, good afternoon. I'm Vishalini, lecturer at Slate Nodorjani. So, I'm presenting our work on AI first operating system. The motivation stems from a growing mismatch between traditional monolithic OS kernel, which are CPU centric, and AI/ML workload that depend on heterogeneous accelerators such as GPUs, TPUs, and FPGAs. Our goal was to systematically analyze how the artificial intelligence can both enhance OS internals and drive new OS architecture purpose-built for AI. So, in the introduction, in conventional operating system, resource management follows deterministic rule-based logic, well suited for predictable CPU tasks such as a process scheduling or memory paging. However, the modern AI and ML workload are highly dynamic. They depend on heterogeneous accelerators like a GPU, TPUs, and then the FPGAs, and exhibited data-driven nonlinear execution patterns. So these workload break the static assumption of legacy kernel, leading to underutilized accelerators, queues, imbalance, and increased latency. Therefore, the emerging research direction is toward AI-first operating system kernel that integrate reinforcement learning, machine learning-based I/O optimization, and adaptive scheduling, making the OS capable of self-tuning its own preference in real time. So the traditional kernels assume predictable workload and rely on static heuristics. In contrast, AI/ML jobs exhibit high temporal variance, deep dependencies graphs, and heterogeneous accelerators usage. As a result, classical round-robin OCFS schedulers underutilize CPUs and caches queue imbalance. Therefore, the OS itself must evolve into an adaptive control system capable of self-learning optimal resource policies in real time. So we adopt a systematic literature review methodology. Each paper was analyzed against 5 quantitative and qualitative dimensions. The taxonomy word driven enable us to separate micro-learner optimization like a reinforcement learning scheduler from macro-architectural proposals such as the AIOAs and MalOAs. This approach expresses both maturity level and research gaps in AI-driven OS domain. So at the subsystem level, a reinforcement learning schedulers dynamically tune CPU quantum based on runtime feedback, outperforming static policies in throughput and energy metrics. KMLib, a kernel-integrated ML library, demonstrates feasibility of embedding lightweight models directly inside Linux kernel space with minimal memory footprint. However, integrating models at kernel privilege raises debugging and determining issues, particularly in the safety critical domain. So the second finding of our CPU scheduling has become the most active subfield. LitOS introduced the lightweight OS like layer on GPUs enabling kernel level preemption. Shallows introduced iteration level context switching for deep learning jobs, achieving up to 42 times through output gain. Teams optimize fairness across multi-tenanted culture using hierarchical scheduling, but yet none of these frameworks achieve hardware portability or that unified fairness guarantees, including scope for OS level abstraction of accelerators. So the building on observed gaps, we conceptual a layered AI first OS model. At the kernel layer, reinforcement gains performance resource allocation with continuous feedback loops. System service integrate fault tolerance, explainability, and trust mechanism to make automated decision auditable. The upper layer exposes standardized APIs for AI framework, effectively making OS both enable and AI enabling. A cross-mapping of 25 papers shows no framework achieving parity across all evaluation metrics. Performance gain dominate, but explainability and portability remain under-addressed. This indicates that future OS research should combine controlled theoretic learning with formal verification and XII technique use at kernel level. So in the conclusion, in a summary, AI can transition operating system from passive resource to autonomous decision makers. Future work should prototype lightweight RL agents inside kernel space, extend schedulers across CPUs, TPUs, or that FPGAs, and define standard evaluation benchmarks. So achieving explainability and trust at kernel level will be crucial for real development in cloud and edge area. So thank you. That's all.
And thank you for your presentation. Are there any questions? Okay, let's go with the next paper. The title of the paper is Robotic Arm Control Using Model-Based Reinforcement Learning and a Three-Dimensional Camera for Object Manipulation.
Hello, can I share my screen?
Yes, you can share.
Okay. Minute, please. Oh, okay, good afternoon. I'm Kitipom Bulong from Burapha University, Thailand. Today I will present a paper entitled Model-Based Reinforcement Learning for Robotic Arm Control using 3D Camera for Object Manipulation. So this is the outline of the presentation introduction, model-based reinforcement learning, numerical study, and the real robot arm control, and then conclusion. The introduction, for the robot arm control, we have two tasks. The repetitive task is like we can fix the angle or the movement of the angle of joint of robot arm. So it's not difficult to control. It's just fix the angle move from here to there, some kind like that. But for the repetitive task, the robot arm have to pick some object and put on the other where randomly. So this method used in this paper are suitable for this task. And we use the 3D camera to identify position of object and pick it and put it in the other location, some kind like that. We call pick and paste. And for 3D, this camera is here. So and the robot arm is here. We have to use 3D camera to identify location of target object, and the keeper is on the robot arm. They have to move to know that the location of the robot arm to move to the object. And to talk about the model-based reinforcement learning. And for reinforcement learning, for simple reinforcement learning, we have agent, and the problem is environment. In each, the location of agent or a state that or some kind that we call state, and the agent take action and get the reward. The agent learn how to get the good reward for any state, so that they learn and learn again, and they know that when he is on this state, he should do which action, some kind like that, and they learn from the reward. They learn from to getting the good reward. And for model-based, they it try to model the environment, so that this is the comparison between of the model-based reinforcement learning, and after reinforcement we call model free. It's found that the model-based use spend less number of calculations, some kind like that. So we interested to use the model-based reinforcement learning for our works. In model-based reinforcement, we have to model the environment or the problem, some kind, and the relation between state, action, and reward, some kind like that. So we try to use 3 regression techniques, that's support vector regression, Gaussian process regression, and artificial neural networks. We consider it to compete each other, and the only one in optimization we use particle swarm optimization of PSO. These are three regression techniques. GPR are used covariance between variable, and AN is basic of deep learning, and support vector machine is like linear regression, but we can change the kernel. And this I have a little bit about some support. Okay, and PSO use PSO for optimization. PSO, we use PSO because PSO are fast in searching. This is I run from Python, and for simple square problem, so it's the optimum is 0, 0. The runtime is only 0.06 seconds to finish to search the optimum solution. And for model-based, we use one application, that's GPR or ANN or support vector machine, to model the environment at the first of the at the beginning, early episode, we call episode early searching, some kind like that. The action come from the random action, and then we store the state, action, and next state in the set of solution, some kind of that we call refer buffer. And after that, we model it by any one of regression. This is the full process. After a number of early episodes, we use PSO to PSO in model that from linear from the regression, and for the optimum action and take action, and do it again and again. So the process until the agent is moved to target, or the number of repeated episode, repeated iteration is certified, some kind of that. And at first we use we do the numerical studies to compare the regression techniques. For three regression techniques, I pick the best one for real robot arm control. The pacing task, the first numerical study is pacing task, try to control the end effector to the target. The state is xy, and action is delta x, delta y, and reward data distance between object and target. And the second one is robot arm reaching task. We control the two 2 degree of freedom robot arm to control n effector, to control n effector to move to the target. State is theta 1 and theta 2, including y and z, coordinate y, z, and action is delta theta 1 and reward is distance. This is the target. We random the target, and we compare any irrigation technique. We found that the GPR can do 100% success of pacing and reaching, and ANN and SVR is twice much less than success rate less than GPR. So we pick GPR and also for in model-based RL in real robot arm control. And in real robot arm control, we have 3D camera and robot arms that we have to train the object. We have three one object, target, and keeper represented by hexagon. And in image processing, the size is like this pixel, and we use YOLO V5 for object detection. In YOLO just do only the 2D image, so they can identify just only X and Y coordinate, but we can know the Z coordinate from the 3D camera. This one, so it can know that object, where is object, where is target, and keeper. We can move keeper to take object and put on the target, some kind like that. This is the process of robot arm control that begin, and the Arduino board move the arm. Arduino board get rotate angle from computer and move the robot arm, and then send the 3D camera know that the location of anyone that we have to know, and then coordinate object, target, and keeper back to computer. Computer use Python code of model-based reinforcement learning to identify the environment, modeling, and optimizer to get the optimum action, and which is the rotate angle, and send back to Arduino to move robot arm again. And angle to control, we have four angle to control. And this is the object and target. This is the base of pick and place time. We found that after 100 training if episode like we move up, take the object and put on the target. 36 testing episode, we found that the robot can success rate 100% in both fixing and placing. And just moment I can show the video a little bit. This is they know the first step. They know the position, and people move object target the file constant because they static, but the keeper can move. By step 6 and pick the object, picking, and then move back. This is a placing, put the object on the target. For conclusion, and we found that the GPR and for numerical study, we found that GPI and PSO are contribute the best solution, and then it used for 3D camera, and so it's success, 100% success in cell. GPI and PSO is suitable to be used for model-based in control of robot arm, but it should do for the complex job, complex work, some kind like that. Thank you. That's all for me.
Okay, thank you for your presentation. Are there any questions? Okay, let's go on with the next paper. The title of the paper is Assessment of Software Security Measures.
Yeah, hello. 1 second, let me share my screen.
Okay.
Do you see my screen?
Yes, and you can start.
Okay. So, hello, my name is Ilya Vukatic, and I'm a PhD student in National Technical University Kharkiv Polytechnic Institute, and I'm going to present you a short report based on papers that we worked on with my colleagues, Assessment of Software Security Measures. The growth of information technologies demands more robust security standards than ever before, precisely because the most methods of cyber attack continue to advance. In this landscape, software security is not just a feature, it is the fundamental pillar supporting the confidentiality, integrity, and availability of all data. For decades, one of the most significant tools in our arsenal has been static analysis. This approach is foundational. It allows us a thorough, deep examination of code without executing it. We can perform lexical, syntactic, semantic, and data flow analysis, identifying potential conflicts, security breaches, or vulnerabilities before they ever have a chance to be exploited. Traditionally, this process has relied heavily on one primary mechanism, signature-based detection. Think of these signatures as digital fingerprints. They are specific sequences of code or byte patterns linked to known security incidents or suspicious behaviors. We hunt for these known bad patterns, cataloged in vast databases. These databases are compiled by antivirus vendors, academic researchers, and governmental entities, forming our first line of defense. The problem is that this signature-based model is fundamentally reactive. It excels at finding known threats, but it is failing us against new ones. The process of identifying vulnerabilities through signature matching is not fully automated. It demands significant resources and critically the expertise of skilled professionals. The real crisis, however, lies with evolving malware. Relying solely on signatures presents in MSN's challenge when dealing with polymorphic and metamorphic viruses. These malicious programs, which constitute the majority of new malware, are designed to change their own code. This means that every time they propagate, they create a new signature, one that is not yet in our databases. We are perpetually one step behind, forced to play catch up, and regular updates to our signature databases are imperative, just to maintain this failing posture. This vulnerability is compounded by our modern development practices. Many programs integrate third-party frameworks or libraries. If these components harbor vulnerable signatures, our entire application is compromised from the start. Therefore, safeguarding code during development is essential. The limitation of static analysis led us to develop a second powerful approach, dynamic analysis. Where static analysis reads the blueprint, dynamic analysis runs the machine inside a steel box. It involves executing program code within a controlled, isolated environment, a sandbox, or a virtual machine like VirtualBox or Hyper-V in real time. This method can be divided into anomaly-based detection, which often use machine learning to spot deviations, and pure behavior analysis. In fact, dynamic analysis is widely considered the most effective approach for analyzing the destructive behaviors of malware during execution. But attackers adapt. Dynamic analysis has its own set of critical vulnerabilities. First, sophisticated malware now comes equipped with antiviral machine. Anti-virtual machine, anti-emulator techniques. It detects the sandbox, realizes it's being watched, and simply shuts down, revealing nothing. Second, this method is incredibly resource-intensive. It demands substantial processing power and time, making it difficult to scale. And third, it is prone to false positives. If a legitimate program's behavior deviates significantly from typical patterns, it can be misclassified as a security threat. So we are left within a dilemma. Static analysis is fast and scalable, but it's blind to polymorphic threats and evasion. Dynamic analysis can see behavior, but it's slow, resource-heavy, and easily fooled by anti-analysis techniques. This brings us to the ideas of the hybrid method of analysis. This is no compromise solution. Hybrid code analysis integrates multiple analytical methods, static, dynamic, and semantic, to create a system that is far greater than the sum of its parts. It begins with the analysis of signatures, but immediately continues by combining other parameters from the behavioral model to enhance the analysis. It leverages the advantages of both static and dynamic techniques to more effectively identify and rectify vulnerabilities, defects, and bugs. The benefits are immediate and profound. We see enhanced software security because we can identify a much broader array of vulnerabilities. We see greater efficiency and accuracy, with a reduction in the false positives that plug dynamic analysis. This approach is also more adaptable to the rapidly changing software architectures we all work with, and it is particularly beneficial for a large project with extensive code base. This is not just an academic exercise. The need for this shift is urgent. Globally, 47% of organizations have reported experiences malicious software or cybersecurity breaches. Attackers are targeting web services, browsers, and operating systems, often using social engineering to deploy their code. To put this in context, let's look at the data from Ukraine's State Center for Cybersecurity. Recent reports show a 36% surge in unclean code incidents, which account for 90% of reported breaches. They also show 43% increase in information gathering by attackers. This all happening while new technologies like 5G, IoT, and AI introduce heightened risks, and the post-pandemic shift to remote work has dramatically broadened the attack surface. The hard truth is that our current approach is failing. Protecting the information system of critical state infrastructure remains an unresolved challenge. The site initiating cyber attacks holds the advantage, and malware can often only be countered after its destructive consequences have occurred. We must also be honest about the tools we buy. The advertised capabilities of many antivirus solutions are misleading. The accuracy results we see are often from tests that do not reflect real-world scenarios. There is a glaring lack of official data on the detection of new malware, not just known threats. So where do we go from here? The path forward requires a fundamental shift in our thinking. First, we must adopt a hybrid approach that combines effective static and dynamic analysis methods. Second, we must change what we are looking for. Instead of just hunting for signatures, our focus must be on identifying the polymorphic and metamorphic components of known malware classes. This will allow us to detect new malware based on the recognition of these structures, even if the full signature is different. And third, we must explore new technologies to help us. A key direction for enhancing our system is the integration of methods grounded in fuzzy logic theory. Why fuzzy logic? Because it allows for approximate reasoning. It empowers our system to identify destructive activities even when there is information uncertainty about the state of the system. This is the key to identifying those polymorphic structures in the wild. To conclude, the threats we face are no longer static. They are polymorphic, metamorphic, and built to evade our current defenses. Our reactive signature-based models are obsolete. The future of software security lies in an integrated hybrid approach, one that combines the speed of static analysis with the behavioral insight of dynamic analysis, one that shifts its focus from hunting signatures to identifying the fundamental components of malware, and one that embraces new tools like fuzzy logic to navigate the uncertainty of the modern threat landscape. Thank you for your attention. That's all.
Okay, thank you for your presentation. Are there any questions? Okay, let's go on with the next paper. The title of the paper is Uncertainties and Emerging Uses of Human AI Medical Diagnosis in Collaborative Clinical Practice. Our daughters here. Okay, the title of the other paper is Big Data Analytics for Optimizing Film Distribution and Social Media Promotion. Our daughters here. Okay, I think the authors are not here. So, dear participants, on behalf of organizing committee, I would like to thank you for your scientific contribution to the Congress, and we hope to meet you in next Congresses as well. Now I am ending this session. Thank you.
Thank you. Have a good day.
Have a good
Thank
day.
you. Thank you.
Thank you.